Today we're going to look at two of the most important design principles used in the ROLM CBX, time division multiplexing and pulse code modulation. In the past, you had to dedicate one wire circuit for every discrete voice signal. However, with the application of time division multiplexing, or TDM, the ROLM system allows multiple voice signals to travel along a single digital bus. And how is this accomplished, you may ask? Well, basically by the use of a digital computer and the high-speed division of time. When a call is processed, the computer's central processing unit, or CPU, assigns a series of switching commands to complete the voice path between two telephone extensions. If extension 1 were connected to extension 6, these commands would be, first, extension 1 transmit. Second, extension 6 receive. Third, extension 6 transmit. And fourth, extension 1 receive. These transmit and receive commands are stored in various time slots on a circuit known as the connection table. Through intermittent transmission on two address buses, these commands are made available to the system, each in its own turn. This sequential commanding allows voice information to be transmitted and received at the proper extensions. Now, the ROLM CBX divides time into frame periods, which are 83 microseconds in length. And within one frame period on the connection table, there are 384 separate time slots for storing the switching commands. Therefore, each transmit and receive command is cycled every 83 microseconds, or 12,000 times a second. And here's the process as it appears in normal time. Notice that there is virtually no interruption of the many signals, allowing the switching process to occur along a parallel digital bus. That's time division multiplexing in the ROLM CBX. The computer's CPU assigns a series of transmit and receive commands. The connection table stores and sequences these commands every 83 microseconds. And because of this time division, many channels of voice information can be transmitted and received on the parallel digital bus. Now, when I refer to paths of voice information, this is where the principle of pulse code modulation, or PCM, is utilized. Pulse code modulation is an electronic process which converts analog signals into digital data. At a given phone extension, sound energy enters the system in an analog form, a signal with amplitude and frequency. This signal enters the extension channel and is sampled 12,000 times a second. In extremely slow motion, we can see that each sample of the analog signal is coded into a 12-bit digital code word. The arrangement of binary ones and zeros now represents that sample amplitude. Upon a transmit command from the connection table, this digital PCM word is placed upon the parallel digital bus. And upon a receive command in the next time slot, the PCM word enters the assigned extension channel where it is decoded back into the original analog sample. However, in normal time, analog signals from both extensions will be sampled, coded, switched, and decoded 12,000 times a second, allowing multiple paths of digital data to be carried on the parallel digital bus. These are the basic principles of time division multiplexing and pulse code modulation as applied to the ROLM system. Now, to best understand the practical applications of these two concepts in the call process, let's visit a business firm that is serviced by a ROLM CBX. Dave is about to call Kathy, who's in another part of the building. His phone is extension 228. It is one of 16 extensions connected to this single-line interface group on shelf 1 in the ROLM cabinet. This particular interface group consists of a 16-channel coder, a 16-channel decoder, and 2 8-channel line interface cards. As Dave picks up his receiver, his line interface card senses the off-hook condition, and a change in status is detected by the CPU. Then, the CPU assigns a series of commands to the connection table on the TDM1 card. These commands allow Dave's extension to receive dial tone from the tone generator. Also, a DTMF register is assigned to receive from his extension. As he presses the first digit, the CPU cancels the 2 commands which supplied dial tone. Then, the DTMF tones from his keypad are coded into PCM words by the coder of his group. These PCM words are received by the DTMF register, which converts this information into a new digital code word. With the addition of a transmit command on the connection table, the DTMF register sends this word to the CPU. In this way, the computer concludes that extension 406 has been dialed, and now those commands are canceled. At present, Kathy's telephone is on hook, so the CPU places a command which then causes her extension to ring. At the same time, 2 more commands are assigned which allow Dave's extension to receive ringback tone from the tone generator. As Kathy picks up her receiver, her interface group detects the off-hook condition. With the change in status, the CPU cancels the commands which supplied both the ringing and the ringback tone. Now, with the placement of 4 last commands, the voice path between the 2 extensions is established, and the switching process is complete. At Dave's coder, his analog signal is sampled and coded into a 12-bit PCM word. Upon a transmit command, it is placed upon the parallel digital bus, and in the next time slot is received by Kathy's decoder and decoded back into the analog sample. In the same frame period, her analog signal is sampled, coded, switched, and decoded at his interface group. And with the high speed of time division multiplexing, these PCM words are transmitted and received 12,000 times a second. In this way, Dave and Kathy are able to converse. But remember that the computer has also been handling many other calls besides this one, and up to 150 separate conversations can be carried on the parallel digital bus. That's electronic switching in the ROLM CBX, made possible by the application of time division multiplexing and pulse code modulation.